Welcome. The title of today's notes worksheet is Logarithms. Today offers us an opportunity to go ahead and investigate what a logarithm is, and also to explore some of the skill sets that are required to be successful in this unit. So we'll go ahead and start off with an investigation here, and I'll go ahead and just read from the board. It just says, using a scale to represent numbers. And so I just pasted a little table in here of different animals and their body masses, and I believe these are in kilograms, by the way, not that it matters a whole lot. But here's what I think I'll ask us to do, if you could. Just next to each animal, let's go ahead and put a letter, and then what we're going to do is try to plot these basically on a number line, which is fairly elementary, at least it sounds initially. So if you could, just go ahead and throw A through F on those, and then let's come on over here, and let's get these taken care of. So something along those lines right there. That way you'll kind of know what animal goes with what position on the scale. And so again, what we're going to do is literally just plot the body masses from the blue whale at 91,000 kilograms all the way down to the little hummingbird at 0.003 kilograms. And so what I'd like to do is explore a way to go ahead and represent these on what we would call a linear scale. So we'll go ahead and start that process, talk about the pros and cons of that scale with this wide range of numbers, and then potentially start to transition into what we would call an exponential scale. So I guess what we need to do is at least start off from a very small number. At least we have to get that hummingbird on there. So I guess it kind of makes sense to start here at 0. So if you don't mind, go ahead at the end, put a little 0. And this doesn't have to be perfect by any means. Just do the best you can with this. But remember what linear means, essentially, that the rate of change is constant. So basically what needs to happen on my scale of numbers, this number line essentially, is I just have to go up by the same amount and keep my increments relatively consistent here. So I'm going to go ahead and go up by 10,000s just because I see we're going to have to get up to 91,000 eventually with this blue whale. So I'm going to go 0 to 10,000. Again, notice the difference between those two tick marks. And so I'm going to try to repeat that and make it 20,000. And let's go get them. So 30,000. And as mentioned, it doesn't have to be perfect, but try to do it as nicely as possible. And if you run out of room or if you have a little extra room, just add on or cut it off. It doesn't matter a whole lot. So let's see, just want to make sure I've got everything squared away from my end. So I'm at 70, 80, 90, and I'll just go a little further out there, and I'll go out to 100 grand. And that's fairly arbitrary. I was just kind of looking at my numbers, where I started and where I had to get to, and that's decent. You know, you can kind of see my tick marks are basically evenly spaced, which is imperative for a linear scale, and notice I'm going up by the same amount. Okay, well, no big deal. So, you know, you've been doing this probably since elementary school. Let's go ahead and plot these numbers on the number line. That's all it is. So I take my 91,000 there, and here's where it would be on our number line, and I'm just going to go ahead and put a little A on top of that, and that's looking nice, no big deal. And then it drops from 91,000 to 5,450, so let's go ahead and throw that one in. The African elephant looks like about right there, give or take, doesn't have to be perfect. White rhino right behind that at 3,000. The hippo coming in at 2,520, something like that. The black rhino coming in at 1,170, something like that. And what do you notice is happening here as I start to go further and further down? I'm going to get my 700 in, and then my 180, and my 70, and 11, and 1. Very different numbers. But what happens when I start to try to put that all on this number line, do you see that it starts to get pretty convoluted? Like, I can't distinguish from one to the other the way this is laid out here. Even though these numbers are dramatically different, take a look at that, guys. These numbers are so incredibly different, but yet you would never know that on my number line right here. This is getting messy, isn't it? Issues. So I guess I would say to you, or ask you the question, is a linear scale the best way to represent such a broad range of numbers? And it doesn't seem to be. Now, potentially you're thinking, all right, well, Mr. Meyer contrived this here. What if we took the blue whale out and started all over again so I didn't have to go up to 100,000? Maybe if we just got rid of that one and did all these, would it work better? And you can try this, certainly, but the fact of the matter is if you did a linear scale with even just getting rid of that top number right there, you would run into the same problem. The numbers are just too broad for us to represent them and to distinguish them properly. And so what we're going to do is explore a secondary way to pull this off with what is called an exponential scale. So I'm going to just get this moving along here. We're going to go with our exponential scales in a particular base. As a matter of fact, I'm going to go ahead and work in base 10 as we work in a base 10 number system. So just kind of playing this out here, the lowest number, just FYI, we're going to go 10 to the negative third, which happens to be 1 over 10 to the third, which happens to be, by the way, 1/1000th. And you can see the hummingbird is kind of coming in at 3/1000ths. That's sort of where I come up with that number, just FYI. Now, similar to a linear scale, I'm going to keep my tick marks evenly spaced, but instead of going up by the same amount, I'm going up by the same power. So the next one, everybody, is 10 to the negative second. I'm going up by a factor of 10. So I'm not going up by the same number, I'm going up by the same factor. So that would be 10 to the negative first. Next one would be 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and by the way, that's as high as we need to go right there, 10 to the fifth. And notice in this particular case, am I going up by the same amount like I did in the linear scale? No, absolutely not. Here I'm going from 10 to 100, here from 100 to 1,000, here from 1,000 to 10,000, so you can kind of see I'm going up not by the same number, but by the same factor. That is definitely different. Okay, now neat. So here's the question, of course. How do I figure out where to plot these particular values on my new scale, my new number line? And so let's think about it just for a little bit here. 91,000, guys, the blue whale. All right, so let's figure out where that fits in terms of our powers of 10. Well, I think I left off when I was talking about this at 10 to the fourth would be 10,000. 10 to the fifth, everybody, of course, would be 100,000. So I'm hoping you would agree that 91,000 is obviously in between 10,000 and 100,000, closer to the 100,000. And so I'm hoping, if I'm going too fast for you, my apologies, but I think that blue whale's got to go right about there. So at 91,000, it's just below 100,000. And that fits pretty nicely right in there. Now let's start to estimate some of these others here. Let's see what we can do with this one. The African elephant coming in at 5450. So what would that look like on my scale? Where am I going to put my B? Well, let's see. So 10 to the third, everybody. 10 to the third is 1,000. 10 to the fourth, of course, is 10,000. And so 5450 is in between 1,000 and 10,000. And so what we want to do is go ahead and place it somewhere in here. And so I'm seeing the African elephant. I'm going to go ahead and just throw it into the mix right about there. But in between 1,000 and 10,000. Does that sound right for this number? It hopefully does. Let's get a couple more going, and then we'll talk about the mathematics behind this, of course. So how about the white rhino? Where's the white rhino fitting in at 3,000? Well, I have a feeling it's in the same two powers of 10. 1,000, 10,000, probably a little closer to the 1,000 here. So something like that. And the hippo, of course, now starting to get pretty close. So the hippo at 2,520, again, just above 1,000. Here's 2,520. And so you could see something like this right here. And as I move down, do you think that we would probably be quite a bit more evenly spaced throughout my number line? And do you think I'd be able to distinguish a heck of a lot better than I was over here? Most likely. So I guess the question then becomes, how do we pull this off? And so I'm going to go to my next board for just a second, and obviously I'll have to come back to this piece. But it says it obviously on your notes worksheet. How do we calculate rather than estimate where the values would be placed on the scale, on our number line? Well, I'm hoping everybody would be in agreement that, in essence, guys, I'm looking for kind of what exponent it would be. So I'm kind of looking in between which powers of 10 our number would reside. And so the question is, how do I kind of figure out in between which two exponents and closer to one number compared to the other, what would I be looking for? And so when we are looking for the exponent, and again, I'm hoping you agree that's exactly what I'm looking for, we need to apply a particular operation. And that operation where we need to find the exponent is a logarithm. And so here's what you're going to write here. Long story short, we're going to take the logarithm of each number. And that's how we're going to apply this. Obviously, stay with it. If it's clicking for you, great. And if it's not, please give it time. But that's basically what I'm going to do. I'm going to take the logarithm of each number. And when I take the logarithm of each number, it should tell me the exponent that I should place it near. So let's give it a try. So I guess I was on the black rhino. And I'm hoping you would agree the black rhino is just over 1,000. So it's probably, in terms of the exponent, in between the 3 and the 4, right? Here's 10,000. Here's 1,000. Here's 10,000. And 1,170 is probably really close to the 3 in terms of the exponent. So what I'm going to do is bring up my calculator here and watch it unfold, everybody. So guys, let's go ahead and hit that log button on your calculator right there. See it? So I'm going to take the log of 1170, and look what I end up getting. Does that seem reasonable for what I was talking about? I was looking for the exponent, and I said it was probably close to the 3, in between the 3 and the 4, and there it is. So log of 1170 is about 3.06, and there it is. It gave us the exponent to place our number. And that's it. So the E probably goes right about there, give or take. Let's do a couple more, get just a feeling for it, and then we'll just move on. I'll probably ask you to finish it up. So where's the horse going? So in between which two exponents would it reside? And let's go ahead and figure it out. So log, the horse is 700, log of 700, and so about 2.85, give or take. And does that make sense for what you were thinking here if I asked you to estimate it? So 2.85 would be right about there. And you can kind of see, of course, 10 to the second is 100, 10 to the third is 1,000, 700 is probably right about there, in between 100 and 1,000. Kind of cool, huh? So we have an operation that allows us to get the exponent in order to place our numbers. And that's the context we're using it for right here, obviously. So I guess maybe one or two more here. And then I'll ask you to pause the video for just a second and kind of finish that up. But let's do that lion there, the lion coming in at 180. So think about where that would probably reside if I asked you to estimate it. And there it is, about 2.26, give or take. And so 10 to the second is 100. And so 180 is just a little beyond the 2 there. And so there you go. There's your lion right there, between 10 to the second and 10 to the third. All right. Well, again, I'm going to ask you, if you don't mind, can you pause the video just at this stage and just take the logarithm of these numbers right here, and that'll tell you where to place it on the scale. And do you see how much more evenly spaced this is compared to this monstrosity right up here? This was a disaster. And that's actually one of the primary usages of logarithms, is finding a better representation of a very broad range of numbers, from 91,000 all the way down to 3 1,000ths. So that's really cool. So we'll see some applications with logarithms, and it'll probably fit along the lines of this investigation here. Okay, so how do we calculate rather than estimate where the values would be placed? Take the logarithm of each number. All right, just a little note and a quick summary, and then we move forward. So it says, note, if we eliminated the base 10 on our exponential scale and used the same values, we would call this a logarithmic scale. As we will soon see, logarithmic scales are widely used to better express a very broad range of numbers. Again, just like the investigation. So, sorry, just real quick here. Instead of doing 10 to the negative third and 10 to the negative second and 10 to the negative first, if I just did negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, and placed them in the same way that I did, that would be called a logarithmic scale. And we'll be using some applications dealing with exactly that piece. Wonderful. All right, so let's summarize and move on. And here's, I guess, a good way to talk about it. So when the exponent is the variable, and I am hoping it was very clear that that's what I was trying to find. I was trying to find the exponent that I was raising this base 10 to in order to place my numbers. So when the exponent is the variable, and I guess for our investigation here, it was sort of the unknown. I didn't know where I was raising those base 10s to. So when it was the unknown, we take the logarithm, and we'll talk about all different types of bases of logarithms, but for right now, we did what was called a base 10 logarithm to get its value. And that's pretty much what we did. I think that summarizes it beautifully. So when the exponent is missing, we need to take a logarithm in order to get its value. All right. Now, one very, very important skill for this unit, as it says on your paper, is writing an equation using its opposite operation. So I don't mean to dumb this down too much or to oversimplify things, but I do want to just kind of give you an example of this before we hit the backside with these new operations. So, seems kind of silly, but do me a favor, kind of box this up right here. This obviously is a perfectly valid equation. 7 plus 3 equals 10. Now, here's the idea, is this equation can be written using its opposite operation. If I bring that 3 on over to the other side, as soon as the 3 travels beyond this equal sign right here, bear with me if you could, as soon as this 3 travels beyond this equal sign, it changes from a plus 3 to its opposite, which of course is minus 3. So I can write this exact same equation using its opposite operation. Everyone cool with that? Addition, subtraction. Two things that mean the exact same. I can also do the same thing with multiplication and division. Again, bear with me just one moment. There's a reason behind this, of course. And you've done this before, where basically if I move this 4 on over to the other side, as soon as it moves beyond the equal sign, it changes to its opposite operation. Really, basically, it moves from multiplication to division, right? And there it is. Now it changed to division of 4. So, two equations written with opposite operations, and they mean the exact same thing. We're going to do the same with logarithms and exponents. And so let's go get the back. So, again, total important skill set, and we want to perfect it here. We want it so it's just totally automatic. Examples 1 and 2. What you have for example 1 are 3 equations written in what we would call logarithmic form. And what we're going to do is write it using its opposite operation, which would be exponential form. Now, I've got a really silly way to kind of remember this and how to do it, and that's what this little hint is all about. So bear with me, but it works. It works. I don't want to use the word stupid, but as silly as this little way that I'm going to teach you is, it's one that I think will stick. So here's the idea, very simply. This is an equation in logarithmic form, and I want you to actually envision in your mind a log, if you would. So here's what you're going to picture. Picture yourself standing on top of a hill. All right, you're standing there, and you have a log in front of you, and you give the log a little kick. And what happens to that log when you give it a little kick and you're standing on top of the hill? It rolls. And that's all I want you to write right here. You are going to roll the log. Bear with it. I promise it'll work. So the hint is to roll the log. All right? So this log, what you're going to circle for me is the base of the logarithm. And by the way, we would read this equation, everybody, as log base 8 of 2 equals 1/3. That happens to be a true statement. Log base 8 of 2 is equivalent to 1/3. What I would like to do is see this exact equation using its opposite operation, which would be, of course, exponential form. So what you're going to do for me, again, is circle the base, and that's what you're going to kick. So this is what you're envisioning on top of the hill. You're going to kick it, and it rolls on over. It rolls, it rolls, it rolls. Okay, so it rolls on over to the other side. Now, when it rolls on over to the side, a couple things happen. First of all, the 2 pops up. Sorry about that. So the two things that occur, number one is when that 8 moves over, the 2 kind of gets freed up there, and the 2 stays right there. Now here's what happens. Here's the key thing. As that 8 moves over to the other side, as soon as it passes the equals, just like we saw with those other operations, it changes to the opposite operation. Instead of being the base of a logarithm, it becomes the base to this exponent right here. So it pushes this 1/3 on up, and that's the equation. And as a matter of fact, this equation is identical to this one, just in its opposite form. And so as a matter of fact, 8 to the 1/3 is equal to 2. To the 1/3, by the way, means cube root. And so that's what you have. Those two things mean the identical thing. Beautiful. All right, let's try it again. Not sure if you've ever seen this before, but when there's not a number right there, when you just have log of 0.01, this is what's called the common logarithm, which we'll see later on in this worksheet, which would be base 10. And so go ahead and just put a little 10 right there for the time being, and circle the base of that logarithm, which is the 10. And again, envision yourself giving it a kick. And when it kicks, it rolls on over to the other side, and there we go. It rolls on over. Two things happen. The 0.01, or 1/100th, kind of gets freed up. And then everyone, as soon as this passes the equals, it changes from the base of the logarithm to the base of this exponent right here. So it pushes up that -2, and that would be the case. If you were to type log of 0.01 on the calculator, you get -2. In fact, I'm going to go ahead and do that as I have a quick moment. So here we go, guys. Watch this. Log 0.01. It equals -2. So that statement obviously was true. This one is also true. Watch this. We're going to do 10 raised to the -2nd, and you get 0.01. So again, two different equations that represent the same mathematics. Cool. Two different ways to express it. All right, let's try one more. Hopefully now, by the third time, it's really starting to click. Circle the base. So this would read log base 1/2 of 4 equals -2. And it's time. So that's what you kick. It rolls on over to the other side. And when it rolls, the 4 gets freed up. And as soon as it passes the equals, it changes from the base of the logarithm to the base of that exponent right there. And so it becomes 1/2 to the -2nd is equal to 4. Cool. And I'm going to go ahead and just put that in parentheses for my own benefit, but that looks great. And that's it. We want it to be absolutely automatic. All right, let's go get example 2 and reverse it. So example 2 now says write the equation in logarithmic form. So notice A, B, and C. I have 3 equations in exponential form. All 3 are legitimate. What I want to do is write the equivalent statement in its opposite operation. So here's what I'm going to do. You always circle the base. That's the key. Always circle the base. So the 3 is the base. And here's what happens. Very similar in nature. So it's going to roll. That's what you kick to the other side. Two things happen when you do that. Everybody, the 4 drops down. So that's perfect. The 4 is right there. Now here's definitely the idea. Hey guys, when that 3 passes the equals, it changes. That's the key. That's what you saw on the front side. It changes to its opposite. So instead of being the base to this exponent, it becomes the base of a logarithm, and that's what we have. So it becomes log base 3 of 81. And if you were to take log base 3 of 81, as we'll explore in just a little bit, that is equal to 4. Okay, good. Let's go ahead and do it. 2 more. Circle the 2. So circle the base always. In either form, you circle the base, either the base of the logarithm or the base of the power, essentially, the base to that exponent right there. Here it goes. It's rolling. It's rolling. It's rolling. So when it rolls, the -5 comes down. It's freed up. And as soon as it crosses the equals, it changes from the base of this -5 as the exponent to the base of the logarithm of 1/32. And so log base 2 of 1/32 is equal to -5. Fantastic. One more. Let's do it. Circle that 16. By now, it's really hopefully starting to click. Again, it seems like a strange skill set, but it is the most important skill set for this unit. This we want to be automatic. As we get into stuff that gets a little more complicated, we need to be able to pull this off. So how about the 1/4 coming on down nicely? And there it goes. The 16 travels. It crosses the equals. So now it changes, and it's log base 16 of 2. And as a matter of fact, log base 16 of 2 is 1/4. And there you go. Either one. So please get some practice on this piece and just automatic, circle the base, roll it, and change the form. Excellent. Hey, now it's time to start getting into logarithms as an operation. And so let's use everything that we've kind of learned in this lesson so far and put it together. And let's see what you know about exponents. That's going to be the key. So here we go. Evaluate each logarithm. And one time only, I'm going to kind of play it out all the way through. And then, I'd ask you almost to pause the video for a little bit and see how much you can pull off here. And then come on back and then listen to the explanation behind it. But let's see what we've got. So log base 8 of 64 is equal to some number. This is an operation that we would do, and it is equivalent to something. So it's equal to a particular value. I obviously want to know what it is. And so for right now, just at this stage, everybody, what I'm going to do is think of it as it's equal to some number, and I don't know that number, so I'm just going to call it x. Now, if I asked you to look at this equation and to write it in its opposite form, you would all probably go ahead and take that 8 and roll it on over to the other side, just like we did, and the 64 would kind of go here, and you would say, all right, now that 8 changes, and that's basically what you're looking for. So if you kind of think about our answer to this logarithm, and again, this shouldn't come as a surprise based on the investigation, well, basically the answer to our logarithm is the exponent for that particular base. So you would ask yourself, 8 raised to the what would give me 64? And when you come up with 8 raised to the second power is 64, then you know that our answer was 2 all along. And that's how we're going to pull this off. So I'm going to just do a little erasing right here and just write our answer in. But basically, log base 8 of 64 is 2. And that's what we're asking ourselves. The base raised to what power is equal to 64? So here's what I have, basically, and this is maybe a little oversimplified, but I think it works. The answer to the logarithm is the exponent for that base. So the answer is the exponent for that base. And if you're not sure what that means, let me run through it just one more time on that. So when you look at a logarithm, you're asking yourself, 8 raised to the what power is 64? Well, 8 raised to the second is 64, so our answer is 2. And that's how it works. Okay, so the answer is the exponent. And that's what we came up with in the investigation. When I needed the exponent, I took the logarithm of those numbers. Cool, well let's go get these. So when I see log base 3 of 27, what I'm really asking myself is 3 raised to the what power is 27? And 3 raised to the third power is 27. So the answer is 3. Now just one thing to note, because I've seen students do some weird things over the years, don't write that. That's not your answer. You're thinking, oh, the answer is 3, and the exponent's 3, so it's 3 to the third. No, 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 no. The answer is just the exponent. So when I ask you to evaluate these, the answer is 3. That's the key. 3 to the third is 27, so log base 3 of 27 is equivalent to the number 3. Cool. Notice what goes on here, and if this throws you off, put a little 10. So think about your powers of 10. We did the investigation. 10 to the what is equal to 10,000? So if you remember your powers of 10, look at the 4 zeros, by the way. So 10 to the fourth is 10,000. So as a matter of fact, log of 10,000 is equal to 4. That one I can do directly on the calculator, so I'm going to go ahead and do that as a matter of fact. Watch this, guys. Log 10,000. And it's 4. Exactly for the reasons that we had specified. So this to the 4th is 10,000. And so our answer is 4. All right, now they get a little harder. Actually, it'd be great if you could, and if you don't want to, that's fine. If you could pause the video, and it looks like I've got 9 remaining, see if you can pull off the remaining 9. That would be ideal. And if you don't want to, hey, no harm done. Well, maybe you did, maybe you didn't. But letter D says log base 4 of 1/16. So you're asking yourself, 4 to the what power is 1 over 16? Well, here's what's interesting about these fractions, and we've seen these before. If this was just 16, you would say 4 to the 2nd is 16, so the answer would be 2. But how do I get a 1 over situation using an exponent? And do you remember? How do I create a 1 over the 16? What type of exponent is required, everybody? A negative exponent. Negative. So 4 to the negative 2nd would be 1 over 4 to the 2nd, or 1 over 16. So don't forget, negative exponents there, so your answer right here can be negative. Okay, letter E. 6 raised to the what is equal to 6? Well, 6 raised to the 1st is equal to 6. And so our answer is just 1. And by the way, if these were any numbers, well, generally speaking, any positive numbers, would it work? Log base 8 of 8, log base 20 of 20, would I always get 1? Yeah. Ooh, how about this one, letter F? Good one here. Let's see if you remember your exponential rules. 2 raised to the what is going to be equal to 1? How do I get an answer of 1 using an exponent? What type of exponent is required? And this is what is called the zero exponent rule. Excellent. So 2 to the 0 is equal to 1. And by the way, within reason, if this is any particular base, as long as it's log base something of 1, should get 0. Watch what happens when I go ahead and just type in log of 1 on the calculator. Here we go. Come on, log 1. Look at that, 0. Anytime the input of the logarithm is 1, you're getting 0 because anything to the 0 is equal to 1. Awesome. So you really, again, need to know your exponential rules for this. How about this one? Log base 3 of 1/3. Well, if this was log base 3 of 3, I would say 1. But how do I get a 1 over 3? Well, again, just like we saw up here, we use a negative exponent to produce a 1 over. And so as a result, 3 to the negative 1st is 1 over 3. And so our answer is negative 1. Ooh. All right, watch H. Log base 4 of negative 16. So I need 4 raised to some power in order to give me negative 16. How in the world are we going to do that? So think about it. 4 to the 2nd is 16. That obviously doesn't get us there. 4 to the negative 2nd, and 4 to the negative 2nd is 1 over 16. Oh, geez, still a positive number. I don't know, 4 to the 1/2. We'll talk about that in just a little bit, but 4 to the 1/2 is actually 2. Notice, in this case, I'm always getting positive answers here. Is there anything I can raise my base 4 to in order to get negative 16? No. And as a matter of fact, that's undefined. And so we'll conclude this piece in just a little bit, but log base 4 of negative 16 simply can't be done. There is no exponent that allows me to get the logarithm of a negative number. How about this one? Log base 2 of 0. Yikes, let's see. I'm just going to play around a little bit. Well, 2 to the 1st is 2. That doesn't work. 2 to the 0 is 1, just like we saw up here. That doesn't work. Oh, geez. Is there anything I can raise my base 2 to and make it be 0? I don't see it. And so as a result, and this is going to definitely come into play on the next few lessons there, so keep this piece in mind. Can I take the logarithm of a negative? No. Can I take the logarithm of 0? No. Okay, let's move it along. J, K, and L. Log base 2 of 2 to the 1/3. So I guess what you're asking yourself is 2 raised to the what is equal to 2 to the 1/3. I'm going to need to see that. 2 raised to the what is equal to 2 to the 1/3. Is everyone okay with me kind of thinking about it in those terms? And what is the what have to be, basically, in order for this to be true? Well, it looks like this has to be 1/3. 2 to the 1/3 would be 2 to the 1/3. And so as a result, I think your answer is 1/3. Nice. If that one doesn't click, that's all right. That's a hard one right there. But think about it in those terms. Your answer is the exponent for this base. Ooh, good one right here. Curious if you happen to remember this from previous courses. What's another way to represent the square root of 3? I'm going to write this. Well, the square root of 3 is actually an exponent. It's 3 to the 1/2. That's actually the case. So square roots can be written as exponents. And as a result, log base 3 of 3 to the 1/2, what do you think here? 3 raised to the what is 3 to the 1/2? Well, I think the what has to be 1/2. And there you have it. Good. And then last one, here's a fascinating one, again coming off of this piece. Well, log base 8 of 64, that's how we started it, is 2. What's log base 64 of 8? Oh, goodness. Well, I don't know. 64 to the what? So 64 to the first is 64. 64 to the second is just going to make it larger. Anyone happen to remember what the connection is? And I'll give you a hint. Think of this one. Remember, everyone, a square root, or a root in general, can be written as an exponent. So how does 64, or the square root of 64, equals 8 sound? Which would be 64 to the 1/2. And that, everybody, is your answer. So a good hard one right here. 64 to the what is 8? To the 1/2. Okay, well, again, you're just going to have to get a little practice on that piece. But let's conclude this and start to bring this whole thing to a general conclusion. But let's write a couple things in here. What I saw from this particular exercise set is, first and foremost, we can't take the logarithm of a negative number or a 0. Look at your answers from letters H and I. Now, our answers can be negative or a 0. But what we would call the inputs of the logarithm, and I'm going to go ahead and circle that and that, those just simply don't work. That's what I mean by we can't take the logarithm of a negative number or 0. That's different than right up here. I can take the logarithm of 1/16. I can take the logarithm of 1. And we'll expand on this on the next lesson, of course. Also, just FYI, don't forget roots can be written as exponents. That's the key. So I'm just going to write this below here if you have an opportunity. So square root of x is really x to the 1/2. Cube root of x, everybody, is x to the 1/3. So don't forget about that from your previous courses. That would be the case. So roots are exponents. And so as a result, when you see this right here, make sure you're able to represent it accordingly and maybe have a shot at that. Fantastic. This is some great, great mathematics. Let's do 4 and kind of put this generally, let's get some closure on this in the next few. So those were great examples for 3. A great exercise set. They all worked out perfectly, as a matter of fact. Not every logarithm is going to be a nice integer or a nice easy rational number there. So what about this? Log base 2 of 20. So what I need you to do is put a little approximate symbol on this. And this doesn't have to be perfect by any means, but I'd ask us, think about what this means. Log base 2 of 20. What you would ask yourself, and this is the key part, is 2 raised to the what would give me 20. So let's talk about powers of 2 for just a second. 2 raised to the what is 20? Well, 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. Okay. 2 to the fifth is 32. Doesn't this sort of remind you of the investigation with all the body masses? Isn't it very similar in nature? And so in this case, when I'm doing log base 2 of 20, I'm asking myself, 2 raised to the what power is 20? Well, what do you think, guys? You know, in this case, here's my 20. 2 to the what is 20? That's what I'm trying to find out. And do you see that it's definitely in between the 4 and the 5 because of that right there? And do you think it's going to be closer to the 4 or closer to the 5? What would be your guess? Well, it looks to me like 20 is closer to 16, and so our exponent is probably going to be closer to 4. Now, I did this on the calculator. You can do this on the calculator. I'm not going to tell you just yet how to pull that off. That will be definitely dealt with. But the calculator pretty much told me about 4.32. If you put 4 point anything and it was within reason, it's great. You know what you're doing. Okay, let's try one more. Log base 5 of 100. All right, well, 5 to the what is 100. So let's go through powers of 5. 5 to the first is 5. 5 to the second is 25. Okay, that's interesting. 5 to the third is 125. And 100 is obviously in between those two. So I'm asking myself, 5 to the what is equal to 100? So I'm hoping you can see it's in between 2 and 3. And it's got to be probably closer to the 3. And as a matter of fact, again, the calculator gave me about 2.86. Does that sound reasonable? So remember, the answer to the logarithm is the exponent in that base. That's the key. I'm hoping that's really solidified at this stage. Cool. 2 buttons on your calculator that we're going to be using quite a bit, so let's just get comfortable with them. We work, as I said, in a base 10 number system, 10 digits, 0 through 9. So the base 10 logarithm is what's called the common logarithm, and that's the log button on your calculator. Okay. And that's what we did the investigation in and all that stuff. Also, we have what is called a natural logarithm, and that would be using the base e. E happens to be a number used quite a bit with exponential functions, and so we're going to go ahead and see that connection to logarithmic functions in the same base. And so because the base e is so prevalent working with exponents, that we have the natural logarithm as well to match it. And so the natural logarithm on your calculator is ln. When you see this ln, it is log base e. That's what it means. But you won't write it like this, you'll write it like this. So let's use that piece to just do example 5 here. These are 2 equations that actually fit perfectly. And one is in exponential form, we'll convert it. One is in logarithmic form, we'll convert it. So guys, let's get moving. One last time, as I said, this we need to perfect. Circle the base, everybody. In this case, this is a base e exponential equation. So circle the e. Now please just be very careful with this. Don't lose steam on me at this stage. Again, roll it on over to the other side. When you roll it on over to the other side, the 0 pops down. And as soon as that e travels beyond the equal sign, it changes from the base to that exponent to the base of a logarithm. Instead of writing log base e, we write ln for natural logarithm. And this is actually a true statement. Obviously, e to the 0 is equal to 1. And what that means, of course, is the natural log of 1 is equal to 0. And watch just real quick, just in case. Natural log of 1 is equal to 0. Cool. One more. If it helps you, and it's kind of silly to do it, but if it helps you, put a little e right here, because that's what this is. Log base e of 5 is just about 1.609. So take that e, and let's roll it on over to the other side. Okay, when it does, the 5 comes out. And as soon as that e travels, it goes across, it changes from the base of the logarithm to the base of that particular exponent. And there it is. So please be careful on this. We'll work a lot in base e before the end of the unit. So please look these over. If I went too fast on this last stretch, my apologies. But please make sure you understand that piece right there. Let me go ahead and just type in so you can see. So I guess I wrote initially ln of 5 is about 1.609. So that's what I gave you. What that also means, equivalent, is that e raised to the 1.609, so I do my e raised to. And notice, guys, look at the button. ln is the primary function on that button. The e raised to is the secondary function. And by the way, look right here, look right above it. The log is the primary function on that button. The 10 raised to, because it's the common logarithm, those things go hand in hand. It's really opposite operations. So I go e raised to the 1.609, and notice I get just about 5. Okay. All right, so good stuff. Went a little over there, my apologies, so I'll wrap it up at this stage. Let me know if you have some questions with this, and we'll obviously continue the discussion with logarithms all the way through this unit. Thanks.